In this video, we're going to take a look at the variation of the cosine function. So as theta changes, how does the ratio output for the cosine function change? This is part 2 of a 3-video sequence. If you are picking up this was the first one, you might want to watch the variation of the sine function first because we're going to maybe move a little faster in this one. So what we're doing here is we have this cosine of theta function. We're going to use a circular definition, x over r. And what we are going to concern ourselves with is what happens to the x over r ratio as theta changes. Let me put a couple of values here on the plane to help us out. So over here, if the terminal ray is along the x-axis, we know that cosine of 0 is equal to 1. If the terminal ray is along the positive y-axis, we know that cosine of pi over 2 is equal to 0. If the terminal ray is along the negative portion of the x-axis, we know that cosine of pi is negative 1. And if the terminal ray is along the negative portion of the y-axis, we can say that cosine of 3 pi over 2 is equal to 0. And having those values for the quadrantial angles from 0 to 2 pi, I guess we could work our way around here and say also cosine of 2 pi is equal to 1 as well, 0 radians and 2 pi radians being coterminal angles there. So what is going to happen as I work through my first quadrant? So let's say I have some first quadrant angle that's pretty small, and I choose on it some point xy with a radius of r. And I could calculate the cosine value there. But let's say I rotated that terminal ray up a little bit and chose an appropriate next value, xy, so that the r's stayed the same. So in that particular case, the second x-coordinate would be smaller than the first x-coordinate. Maybe I should label these with some sub-notation here. That on the first point, if I call this x sub 1 comma y sub 1, and this x sub 2 comma y sub 2. The r's I'm going to leave as r's because they are the same. X sub 2 is going to be smaller than x sub 1 in this particular case for for the radius staying fixed. If I did this a third time and now had a terminal ray that was steeper, choosing once again some point on the terminal ray so that the radius for all three of these is the same, and I call this x sub 3 comma y sub 3. The x sub 3 coordinates even smaller than the first two. So of the 3 x coordinates I have, x sub 1 is the largest, x sub 2 would be the middle value, and x sub 3 would be the smallest value. And these are for all increasing values of theta. My first angle is some value of theta. My second terminal ray is a larger value of theta. And the third angle is still a larger value of theta. What I would say here is as theta goes from 0 radians to pi over 2 radians, comma, cosine of theta. So I'm looking for the output. I'm not just looking at the theta. I'm saying, what would the answer to cosine of theta be? Well, it goes back to your definitions and looking at mostly the value of x, because the value of r is going to stay fixed. So as theta goes from 0 to 2 pi, the x coordinates of the points on my terminal ray, x sub 1, x sub 2, x sub 3, get smaller and smaller and smaller. So I have some x sub 1 over r turning into an x sub 2 over r turning into an x sub 3 over r, where my values of x are getting smaller, the values of r are staying the same. So overall, those ratios are getting smaller and smaller. X sub 1 over r is larger than x sub 3 over r. So I can say, if I finish off my statement here, as theta goes from 0 to pi over 2, cosine of theta decreases. It's getting smaller. If I have a ratio, a fraction, x over r, my numerator is getting smaller, my denominator is staying the same, the overall value is getting smaller. And I can even say it more specifically. Not only is cosine of theta decreasing, but it's decreasing from 1, because that's the output for cosine of 0, to 0, because that is the output at pi over 2. And so that's why I can say that as theta goes from 0 to pi over 2, cosine of theta decreases from 1 to 0. Now I can use this idea to not just understand how the cosine function works, but I also can use it to help me remember some of my important values of the cosine function, our special angles, our 30, 45, and 60 degree angles, pi over 6, pi over 4, and pi over 3 radians. And so if I look at the first and third rows of this particular chart here, I can see that I've got thetas that are increasing. And as my thetas are increasing, if I make the appropriate input-output pairings, that those get paired and those get paired, those and those and those, I can see that as my thetas get larger, my cosine of thetas are getting smaller, starting with a value of 1 here and ending with a value of 0 there. Furthermore, I can also, to help me remember, I can do the same thing we did with the sine function, is I can rewrite 1 as root 4 over 2. Then I have root 3 over 2, root 2 over 2. I can rewrite 1/2 as root 1 over 2. And I can rewrite 0 as root 0 over 2. Just a mnemonic device to help you remember these values of these special angles. It is very important trigonometry to be able to quickly and accurately state, what is the cosine of 60 degrees. And to me, when I look at that, I think to myself, okay, cosine of 60 degrees in the first quadrant, it's a pretty big first quadrant angle. So if I have a pretty big first quadrant angle, that xy point on the terminal ray is going to have a fairly small x coordinate. I'm really only concerned with the x coordinate because it's a cosine function. So cosine of 60 degrees, 60 degrees, a large first quadrant angle. Its point on the terminal ray is going to be a fairly small x coordinate. So I know I'm going to have a pretty small output. So I remember that it's going to be 1/2. It's sometimes tough to get the 1/2 versus the root 3 over 2s straight with sine and cosine. So you can use some of that to help you remember exactly what is going on with your trig functions. Furthermore, it can help you derive the graph of the tangent of the cosine function. If I'm going to graph the cosine function from 0 to 2 pi, most of you may have done this at this point, maybe not everybody. But what I know from my quadrantals is that cosine of 0 radians is 1. So I have a point right here. I know that cosine of pi over 2 is 0. And I know the function is going to decrease from as theta goes from 0 to pi over 2, my output is going to decrease from 1 to 0, and so on and so forth. We can use this idea and work our way through the rest of the quadrants as well. And I'll do this for the second quadrant as well here. It's going to be a very similar argument. If you're feeling comfortable with this idea, maybe you don't need to watch the rest of the video. but if you want to hear it out as some reinforcement, it might not be a bad idea. So I want to start with a clean graph here. And what I'm going to do is worry about having an initial ray in standard position, and then once again, terminal rays going through the second quadrant as my theta is getting larger. So I have some theta there, another larger theta, and successively larger thetas. So my statement, once again, it's variation. How do these things vary? I'm just going to say, as theta goes from pi over 2, that's what we're going to pick up from. We're in the second quadrant. Second quadrant starts at pi over 2 radians, to pi radians. The question is, what does cosine of theta do? And that's what we're going to have to answer with very much the same argument. And I am going to choose points on the terminal rays so that the distance from the origin to that point on the terminal ray is the same, and I'm going to call it r, in every case. Now, while I have the same r, these points are going to have different x and y coordinates. So the first point I'm going to call x sub 1, comma y sub 1. The second will be x sub 2, comma y sub 2. The third will be x sub 3, y sub 3, and so on and so forth. Now, the first thing I need to remember is, whoa, in the second quadrant here, those x coordinates, x sub 1, x sub 2, x sub 3, are all going to be negative values. So I'm going to have to deal with some of that. And what I will see here is if I look at these x coordinates, and I only really care about the x coordinates because I'm dealing with cosine, this x coordinate is negative, but its absolute value is pretty close to 0. X sub 2, once again, a negative value, but its absolute value is getting farther from 0. X sub 3, still negative, and its absolute value even farther away from 0. I don't want to say that the x coordinates are getting larger. In fact, the x coordinates are getting smaller because I'm going farther and farther in the negative direction. If I wanted to speak mathematically poorly, I could say, I guess my x coordinates are getting more negative. Doesn't make a whole lot of sense, but if you're struggling and you needed some clarity there, that's one thing you can think of it. So our x coordinates getting farther and farther away from 0 in the negative direction. So quote unquote getting more and more negative. If I make some of these ratios like I had previously, we go from x sub 1 over r to x sub 2 over r to x sub 3 over r for our ratios. Those x coordinates, they're negative, and their absolute values are getting larger, so that the overall value of the ratio, this overall value versus the second overall value versus the third overall value, those ratios are getting farther and farther away from 0 themselves. You go farther away from 0 in the negative direction, your overall values are getting smaller. So as theta goes from pi over 2 to pi, cosine of theta is decreasing. And we know it's getting decreasing specifically from 0. If we look right here, I'm going to shake that around. From 0, cosine of pi over 2 is 0. 2, and we're going to end up over here. So we're going to end up from decreasing from 0 to negative 1. And I can use that idea when I go and derive the graph of the cosine function continued that I picked up, from right here. I started with cosine of pi over 2 equal to 0, And I know that as my theta goes from pi over 2 to pi, my function is going to continue to decrease from 0 to -1, and I get the next piece of my cosine function. These arguments continue similarly for quadrants 3 and 4, just paying attention to the signs, the SIGNS signs of the x-coordinates, and whether they're getting bigger, whether they're getting smaller, whether they are positive, whether they're negative, and you can make similar arguments and talk about the variation of the cosine function. Hope you found this helpful, and if you have any questions, you can ask me in class.